Hi, I'm going to talk about the buoyant force in general and then give you a specific example of how we could apply the buoyant force to make a testable prediction. So the buoyant force is the result of pressure differences between the top and the bottom of an object that's immersed in a fluid. Now you are immersed in a fluid right now. You're immersed in air. The air pressure above your head is a little bit less than the air pressure below you, and you get just a tiny bit of lift on you. But if you jump in water, you certainly notice this effect more dramatically. So let's say we have a cube of some sort, and it happens to be inside some water. Okay, it might be accelerating up, might be accelerating down, might be neutrally buoyant, doesn't matter. At this moment, there is pressure above, there's pressure below, and because there's pressure above and pressure below, there's a force pushing down, there's a force pushing up. But those are different because the pressure below is greater. So there's a difference in those forces. Now on the sides, they're going to be the same. Not roughly the same, they are going to be the same. So and then of course you can imagine the front and the back of this cube having forces upon it. But the front and back, left and right forces are going to cancel out because the pressure is the same at equal depth. But because the top and the bottom are at different depths, they have different pressure and therefore difference in forces. So what we do is we take the sum of all of those inward forces on the object that's immersed in a fluid, we add them up and give it a name. Okay, and that name is called the buoyant force. So adding up all those, we calculate it, or we kind of lump multiple forces together into a single force. Okay? And it doesn't matter if it's a cube or not. It works for a sphere just as well, or any odd shaped object. Okay, so in words, the buoyant force is described as the weight of fluid displaced. So you can imagine the water that would have been in this spot if the cube wasn't there. Its weight is the strength of the upward buoyant force. That's a nice thing to say, but it's not and it's accurate, but it's not a practical way to calculate the buoyant force. The most practical way is to use this formula. Most of the time, this is the useful formula for buoyant force. It's not that weight of fluid displaced is false. It's just that this is usually the information that you have. So what do you need to know? Okay, you need to know the density of the fluid. So if it's water, 1,000 kilograms per cubic meter. You need to know the volume displaced. Okay, if it's completely submerged and there's no pockets of air or anything like that, then it's the volume of the object. If it's on the surface, it would only be that portion of it which is below the surface of the liquid. And then G, of course, is 9.8. Okay, and so this is the magnitude. Of course, the direction is upward. Okay, against the gravitational field. Okay, so yeah, just be careful with subscripts here. Don't drop them. Okay, this is density of the fluid, not density of the object. This is volume displaced, not necessarily the volume of the object itself. Okay, so let me give you an example of using this. Let's say I've got let's say we've got a lump of iron, and we're going to suspend it in water. And I want to calculate based on a few things that we have to know in advance, of course, but I want to predict what the tension in that string is going to be, or you can think of this as the apparent weight of this lump of iron while it's inside there. Okay, and the only piece of data that I'm going to give in advance is that the radius of this sphere is 15 centimeters. Okay, and our goal, calculate the tension in that string. Okay, so we're going to hold this here. How much force do we have to exert in order to hold that lump of iron in place in the water? Okay, now intuitively it's going to feel less heavy than it would in the air, and that's because we have a buoyant force that's kind of helping support that object. Okay, so this is a force problem, so we start with a free body diagram. We would have a weight force down. We would have a tension force up and a buoyant force up. Okay, and I don't know, until I calculate these, I don't know exactly how big to to draw those arrows. But I do know there's 2 upward forces and 1 downward force. So weight force down, again, equal to the sum of the tension and buoyant forces. Okay, so let's turn that into a mathematical statement. We would have total force in the y direction equals 0. Okay, and then I just use my free body diagram to inform the left-hand side of this equation. So tension up, buoyant force up, and weight force down. And now I need to throw in formulas. So T is the unknown here, so we'll leave that alone. So I'll just rewrite T. And then I have buoyant force right here. Density of fluid, volume displaced, times G. Okay, and then I have weight force. Typically we throw in M times G. So minus M times G. Okay, so I'm not ready to solve for T yet because I don't know M. Okay, but if you go back to the definition of density, we have density is mass over volume. So mass is density times volume, but it's density of the object times volume of the object. So this is where subscripts get important here. So I have tension plus, just rewriting the buoyant force once again. Okay, and instead of writing mass, I'm going to substitute in density of the object, volume of the object. Okay, let's go and turn that into minus sign. So density of the object, volume of the object times G. Okay, so now I can solve for tension. But well, actually, one more thing. Before I start doing algebra, I'm going to assert that these two happen to be the same in this case because the object is fully submerged, so the volume displaced is equal to the volume of the object. So now I'm going to deliberately erase those subscripts. Volume displaced and volume of the object for a fully submerged object are going to be the same. If it was halfway in there, of course I couldn't do that. Okay, and then also we're going to have to use a little bit of geometry. The volume is 4/3 pi r cubed. Okay, so I'm going to do the algebra pretty quickly here, but the tension will be equal to density of the object minus density of the fluid times the volume, which is 4/3 pi r cubed, and then we multiply by G. Okay, so yeah, algebra is a little fast, but I just solve for T, substitute in volume of 4/3 pi r cubed. Okay, so next is to throw in numbers. I know the radius, I know which planet we're on, I know the density of the object. We looked that up. I said it was iron at the beginning, and then density of the fluid, water, we can look that up as well. Okay, or maybe you have that memorized. Okay, so density of iron is 7,874 in SI units of kilograms per cubic meter. Density of water is 1,000, and 4/3 pi times its radius of 0.15 times G positive 9.8, and I get that the tension is equal to 952 newtons. Okay, and of course that's how hard you would have to pull up on that string in order to hold this in place. Now you can compare this, if we did just a calculation of this thing right here, the weight force, density of the object times volume times G, you get about 1,090 newtons. So it feels a little bit less heavy than it actually is. Okay, so that's the apparent weight of this lump of iron when it's immersed in water. And of course, the same thing happens to you, right? When you jump in the water, you have an upward buoyant force. It almost balances out your weight. Okay, and so it requires very little force for us to stay on top of the water. Okay, so that's it for today. So thanks for watching. I'll see you next time.